You may remember this mess from the first hand soldering video. Someone is still trying for a quick, easy way to hand solder. By using improper methods, they always seem to end up with unacceptable product. Hand soldering in the attachment of components to printed circuit boards must be done by qualified personnel. A combination of training and experience will give you the knowledge and the ability to use the tools and the materials that produce a high-quality assembly. In the first hand soldering video, we discussed soldering irons, solders, and fluxes. In this video, we will discuss the techniques used to make the hand-soldered connection. We will also take a look at some acceptable and rejectable hand-soldered joints. Most production soldering is done with automated machines that can make hundreds of soldered connections at a time. But many boards still require some hand soldering. Some components are too heat sensitive for soldering machines. Sometimes components need to be removed or replaced. Whatever the reason for doing the job by hand, we must know how to make a strong physical and electrical connection that will last. We'll start with the procedure for tinning the tip of your iron. In the first hand soldering video, we saw oxidation form on the surface of the metals to be soldered. This oxidation will also form on the tip and the barrel of your soldering iron. Oxidation acts as a barrier or an insulator, which means that it slows down the transfer of the heat. Oxidation can prevent a significant amount of heat from being transferred rapidly to the parts to be soldered. To start the tinning process, we'll take the hot iron and wipe it 2 or 3 times across a wet cellulose sponge. This will remove some of the impurities, but won't cool the tip too much. If the tip is wiped excessively, or if it is gouged around in the sponge, it could be too cool to use for soldering or tinning. Now let's apply some flux core solder to the tip. The flux inside the solder will flow first, chemically reducing the oxides from the metal of the tip. The solder will then flow over the tip and form a thin, shiny coating. This tip is now properly tinned. A well-tinned tip transfers heat quickly to the parts to be soldered. Tinning should be repeated as often as necessary. Whenever the tip is no longer clean and shiny, you've waited too long to re-tin. When the iron is not in use, it's a good idea to coat excess solder on the tip and not wipe it off. This prevents oxidation of the tip when it's not being used. Whenever you change tips, the new one needs to be tinned as soon as it heats up. On some irons, oxidation can also form on the barrel, the area between the tip and the handle. If it's not removed, oxidation on the barrel will affect the transfer of heat and keep the tip from quickly reaching its designated temperature. This oxidation may be removed with fine abrasive or a fine wire brush. This should be done away from the board to prevent contamination. Now we'll ask a few questions. Feel free to pause or stop this videotape to ask about anything you don't understand. Now, Let's start soldering. We'll be using a temperature-controlled iron with a pointed tip that develops a tip temperature of 370 degrees centigrade. Our solder will be 6337, that is 1 millimeter in diameter, with a core of RMA flux. To demonstrate the basic technique, we will be soldering a component lead in a plated through hole. This type of hand-soldered connection should normally take only about 3 seconds. We'll start by laying the soldering iron tip against the lead and the land. This will heat both the parts to be soldered. The solder wire touches the tip momentarily, then moves to the opposite side of the joint, touching both the lead and the land. When there is enough solder at the connection, the solder wire is withdrawn with or just before the tip is removed. Let's go through the process again. First, the tip contacts both parts to be soldered. These parts are being heated to a temperature greater than the melting point of the solder being used, but less heat than would melt the base metals of the parts being joined. The parts to be soldered need to melt the solder, but by touching the hot tip momentarily, the solder that flows into the joint will form a heat bridge that will transfer the heat quickly from the tip to the parts. The solder wire is then moved to the opposite side and touches the lead and land. They are hot enough now to melt the solder, which flows over, into, and around the joint. The solder wire is then removed, quickly followed by the tip of the iron. Practice will teach you when there is enough solder for a good connection. This is what may happen if the tip is removed before the solder wire. The tip is removed with or just after the wire. This hand soldering process does a lot in just a few seconds. The parts to be soldered are heated, cleaned of oxides, and joined together to form a solid physical and electrical connection. Perhaps you noticed that we worked on the side of the board opposite the components. This is done to minimize the amount of heat that reaches the component. In some cases, a heat sink or thermal shunt must be used to absorb heat. This thermal shunt is attached to the lead between the area to be soldered and the component to prevent excessive heat from damaging a sensitive component. Now let's review the hand soldering procedure. Remember that wetting is necessary to have a quality soldered connection. As solder flows over the heated parts to be joined, it combines with the surface metal of those parts. There is a molecular combination of the metals called the intermetallic bond. When this combining of the metals occurs, there is wetting. Without wetting, there will be no dependable connection. If the solder joint does not exhibit proper wetting, it's not acceptable. This is an example of what you will see when there is wetting on a through-hole connection. This is a view of a properly wetted joint on the component side. There is a concave surface of solder called a fillet that is flowed or feathered out to a thin edge. Now we will show you some soldered connections that exhibit problems that can be avoided or corrected. This is a cold solder joint. The solder was melted by the iron rather than by the parts to be soldered, and the flux may have burned away. The connection never became hot enough to allow wetting with the solder. Here's another cold solder joint. Notice that the surface of the solder is dull and grainy. The solder does not flow out to a thin edge, and the fillet is not properly concave. This is a disturbed joint. Either the board or the component was moved during the solidification of the solder. It's important to keep the board and the component stable during the cooling of the solder. You can see that the solder is dull and grainy, similar to the cold solder joint. This is a fractured joint. The lead may have been moved after the solder hardened. Clipping the lead too close to the solder can also fracture the joint. Here we have a burnt board, and this is a lifted land. These conditions can occur when too much heat is transferred to the board. Pushing down hard with the iron can also help lift a land. Failure to allow cooling of an area between heat applications can also result in a lifted land. These are visible signs that the iron was left on the board for too long, or that an iron with too high a temperature was being used. But some heat damage may not be visible on the surface of the board. Excessive heat has caused a crack in the plating on this through hole. Differing rates of expansion for the metal platings and the laminate materials have caused this interior crack. This sensitive component was also damaged by excessive heat. There are 3 classes of printed boards, each having its own requirements for acceptability. IPC Video has a tape on solder joint inspection for through-hole components. This video discusses acceptability standards for each of the 3 classes of boards and will answer some questions concerning what is acceptable for the class of boards you work on. Another defect is the blowhole. These are caused by gas escaping through the solder as it solidifies. If there is any moisture or solvent heated in the board, it can create a blowhole as it expands and escapes. This joint has excessive solder. The fillet is not concave, and there is solder flowing over the edge of the land. Too much solder was added to these joints. This condition is called solder bridging. A bridge is an electrical path that was not intended. Here is a solder projection, also known as an icicle or a peak. These problems are typically caused by excessive solder or insufficient flux, and by the iron being too cool or being removed too quickly. These are solder balls. If one or more dislodged, they could cause a short by landing between 2 circuits. Solder balls should be removed. Here we have an example of non-wetting. The solder is not bonded to any part of the lead or land. The solder does not feather to a thin edge. The base metal, the metal of the lead and the land, is partially exposed. There are several conditions that can cause non-wetting. In a few cases, the base metal is not wettable with the particular flux and solder being used. This means that this metal will not combine with the solder. It's possible that the base metals are contaminated or oxidized. Thin oxide films may be cleaned with flux. Some situations may call for a stronger, more active flux. Contamination removal may require solvent cleaning or even mechanical abrasion. Caution must be used to avoid damage to the board or components. We saw non-wetting earlier when we looked at a cold joint. In that situation, there was insufficient heat to create proper wetting. Here is an example of de-wetting. Can you see that all of the base metal is covered with solder? But there is no even fillet, and the solder that has wet the surface has receded in some places, leaving uneven mounds of solder. De-wetting is generally caused by contamination, either on the base metals or in the solder itself. Now let's review some of the solder joint problems we have covered. Now let's look at how to clean flux residues off the board. Some fluxes can leave a residue that will become sticky. This could attract particles that would eventually form a conductive path or short circuit. Other fluxes can actually form an electrical route that will bypass the intended electrical pathways. Sometimes the type and amount of flux used won't create a problem. In these situations, the board may be left alone. If the flux or the class of board requires cleaning, you must know what kind of cleaner to use and how soon after soldering this cleaning must be done. If the flux is a rosin type, the board will be cleaned with a solvent. This should be done with either an ESD-approved bristle or acid brush, a Q-tip, or a dry cloth immediately after the soldering process. The board should be brushed carefully to avoid damage. Often an absorbent material is used to remove the solvent so the residue doesn't just spread around the board. Even then, some of the flux is still left on the board. If the board and all its components are compatible with vapor degreasing, the assembly should then be cleaned in a vapor degreaser within 60 minutes. Some assemblies will be damaged if they are cleaned improperly. Your supervisor will advise you as to which boards should be cleaned and what methods will be used. If a water-soluble flux is used, it should be cleaned with water. Contamination from the flux residue on and in the board is the problem we must avoid. While holding the board at an angle, rinse the area with lots of water. Brush the board well with a bristle brush. If further cleaning is required, the board should be re-cleaned with an aqueous cleaning machine within 30 minutes. With some water-soluble fluxes, the residue can become extremely hard in a short time. If not cleaned within the proper time frame, some residues can become uncleanable. If you need more information, talk with your supervisor or training instructor. Because each company sets its own procedures, there are many variations in methods, tools, and materials. Please stop the tape now and discuss your company's policies for cleaning flux residues off printed wiring board assemblies. We will now leave you with some guidelines for preferred solder joints. The shape of the lead of each part should be visible underneath the solder. All connections must display proper wetting. There should be a concave fillet that tapers to a thin edge. There should be enough solder, but not too much. In some applications, excess weight is definitely undesirable. Although there has been a great deal of information in these two hand soldering videos, a good through-hole solder joint is fairly simple. Now it's time to add soldering experience to the knowledge you've gained here. Good luck!